Hey guys, welcome. Yeah, so problem 5 here, and in part A, what we have to do is determine when the particle P is moving to the left. So that'll mean that we have to figure out when the velocity function for the particle P is less than 0. And what we're given is the position function for the particle P. And so to get to the velocity function, we need to take the derivative of the given position function. So we write that the velocity function is the same as the derivative of the position function for the particle P, and so that means we have to take the derivative of this function here. And so we have to write 1 divided by, and it'll be 1 divided by, this quadratic, right? And that quadratic can be written in vertex form as t minus 1 all squared plus 9. But then we have to multiply by the derivative of this, and that's required by chain rule, right? Okay, and then we'll be done. Okay, so I can multiply by the derivative of this quadratic, which means I multiply by 2t minus 2, or 2 times t minus 1, right? I can write it this way. Okay, cool. Now this here is correctly the derivative of that, and therefore the velocity function for the particle P. All right, and we need to figure out where this is less than 0. So to do that, first let's figure out where it's equal to 0, and it's clear that it's equal to 0 when t equals 1, right? Okay, cool. And so if we do a number line analysis for the velocity function of particle P, then t equals 1 is an important point. So first, the left end of our interval is 0, the right end is 8, and then now we mark t equals 1 as something significant, right? Specifically, it's where the velocity of particle P is equal to 0, and let's label the number line v sub P, because we're doing analysis for the velocity function of particle P. All right, now I chose to rewrite this quadratic there in its vertex form, because in its vertex form we can easily see that the smallest value of the quadratic is 9. That is, this quadratic is never 0 or negative. That's important, because what we're going to do next in this number line is decide on what intervals the velocity of particle P is positive and negative. And those are easy to decide once we figured out where it's equal to 0, right? We just pick a number to the left of where it's equal to 0, and pick a number to the right of where it's equal to 0, and test those numbers in the velocity function, and we can then tell if it's positive or negative on that whole interval to the left of t equals 1, and then t to the right of t equals 1. So to the left of t equals 1, let's pick t equals a half. That'll make this numerator negative, and we already said the denominator is always positive. So we have negative divided by positive, therefore we're going to get negative. So to the left of t equals 1, the velocity of the particle P is going to be negative. And then if we test t equals 2 to the right of t equals 1, then this will be positive, and as I've already said, the denominator is always positive, so we get positive over positive, so we get positive. And therefore, we see that the answer to part A is 0 is less than or equal to t is 0 is less than or equal to t is less than 1. Now, I couldn't say less than or equal to 1 because at t equals 1, the velocity of the particle P is equal to 0, right? That is, the particle is not moving at t equals 1. Okay, cool. That's how we'd answer part A, and let's move to the other parts, parts B, C, and D. All right, we've got quite a lot to do. All right. I'm going to leave the number line up here because we're going to need it to answer part B. So, part B is going to say what? Here it is, so let's find out. Part B is going to say the following, which is, for what time intervals are the two particles traveling in the same direction? Boring, but now it means that we have to do a number line analysis for the velocity function of the particle Q. All right, okay, we'll do it. Here it is, number line for the velocity function of the particle Q. So this is VQ. And then, once we do the same analysis for V sub Q, then we're just going to compare the two number lines and see where on what intervals they're both positive or they're both negative, because that'll mean they're both moving to the right and both moving to the left, and that's all we have to do, right? Okay, cool. So again, this left end is 0, this right end is 8, and the velocity function of the particle q is a nice little quadratic, and it can be factored, so that's even nicer. So we can write it as t minus 3 times t minus 5, and from here we can easily see that it's equal to 0 at t equals 3 and at t equals 5. So we'll mark those. So 3 here and 5 here are where the velocity of the particle q are equal to 0. And so then we test a point in this interval, in this interval, and in this interval. And if we do, then we're going to get the following signs. We're going to get negative here, and then positive in the middle interval, and then we're going to get positive. No, we're going to get positive, negative, positive. You can test. Like, so if you test 2, you get 2 minus 3, which is negative, and then 2 minus 5, which is also negative, so the product is positive. So I was kind of getting ahead of myself. So this is positive here. And in here, if you test 4, you get, like, positive times negative, so that's negative. And then beyond that, you get positive if you test, like, say 6. Yeah? Okay, cool. Now, comparing the two number lines, it's clear that there are no time intervals when they are both negative, but they are both positive when 1 is less than t is less than 3, and again when 5 is less than t is less than or equal to 8. So there's the answer to part B. Yeah? Cool. All right, let's keep it moving to part C now. Part C. What does part C say? Let me first get rid of this, guys. All right. So part C. Part C says this, which is a lot. And it is, find the acceleration of the particle q at time t equals 2 and see if the particle q is increasing its speed, decreasing its speed, or neither at time t equals 2. All right, very predictable, right? Like, they always love asking questions like this. The first part is pretty straightforward, right? Like, so the acceleration of the particle q will be given by a sub q, and since we're not given that function, it's pretty clear what we're going to do. We're going to take the derivative of the velocity function for the particle q. And the derivative of velocity is acceleration. And so that's going to give us 2t minus 8, right? Okay, cool. So at t equals 2, we see that the acceleration of the particle q is going to be equal to 2 times 2 minus 8, which is equal to negative 4. So we've just answered the first part. And the second part is the speed of the particle increasing, decreasing, or neither at time t equals 2? Recall that the velocity of the particle q at time t equals 2 would be like plugging in 2 in here, right? So like that would be 2 squared, which is 4, minus 8 times 2, which would be 16. So 4 minus 16 is like negative 12, plus 15 is a positive 3. So there it is. And I needed to answer about the velocity at time t equals 2 for the particle q, because in order for us to say if it's speeding up or if it's slowing down, which is if its speed is increasing or decreasing or neither, we need to check the value of the acceleration at the same time as the value of the velocity, namely at time t equals 2, and see if they are both negative or both positive. If they're both negative or both positive, then the particle's speed is increasing. But if they disagree in sign, which is when one is negative and the other is positive, then the particle's speed is decreasing. And such is the case here, because the acceleration of the particle q is a negative number, whereas the velocity of the particle q is a positive number. And therefore, because velocity and acceleration disagree in sign, that is, they don't have the same sign, the particle is slowing down. That is, its speed is decreasing, slowing down. Yeah? Okay, cool. All right. So we've got one last part to do, and we will be done. And hopefully the best for last. Let's see. Part D, the final part. What is it going to say? Oh, surprise us, part D. All right. So part D says this, which is find the position of the particle Q the first time that it changes direction. First of all, notice that the first time it changes direction is at t equals 3, the particle Q, because it was moving to the right up until t equals 3, and it started moving to the left after t equals 3. So they're talking about the position of the particle at t equals 3. So what they're asking for is x sub q of 3. Remember, position is denoted by x, right? Okay, cool. But wait, we're not given the position function for the particle q. We're given its velocity function, so that means we have to integrate. And also, they gave us this little piece of information that we have not used up to now. And so we knew that it had to have been for a reason, right? And we can summarize this information right here by writing that it's the same as saying that the position of the particle Q at time 0 is equal to 5. We look at this and we look at this and we think a little bit, especially knowing that we have to take the antiderivative of this, and the evaluation theorem comes to mind, right? We know that x sub q of 3 minus x sub 0, x sub q of 0, we know this will have to equal, since it concerns the position of the particle q, it will have to be the integral from 0 to 3 of v sub q of t dt, right? If we integrate velocity, we know we get position, and if we put limits on our integral, then by the evaluation theorem, what we've written on the left side is correct, and what we're after is this, right? So we could slightly modify what we have and solve for what we want, which is we could write, and what I have here is just the same as what I had, right, with the minus sign, right? This here is the same as this here. I just added this guy to both sides of the equation I modified, yeah? Okay, cool. You get it. Feels like kind of like a magic trick. Anyway, this is like 5, and this is just the antiderivative of like some polynomial, so we could do that. And so let's do that. X sub q of 3, what we're after, is equal to 5 plus, what's the antiderivative of this? It's like t cubed divided by 3, right? And then minus 8t squared divided by 2, so minus 4t squared, and then plus 15t, and then we need to evaluate, and like this is by itself, we need to evaluate from 0 to 3, right? And so if we plug in 3, we get like 3 cubed, which is like 27 divided by 3, that's 9, so we have 5 plus, and then we've got 9, and then 3 times 3 squared times negative 4 is like what? Negative 4 times 9, so that's like negative 36. That's a lot of negatives, so that's minus 36. And then plus 15 times 3, thank God. That saves the day. So that's going to be plus 45, right? And as you can see, like if we plug in 0, all 3 of these guys are going to turn into 0, so no bothering with that 0. Just need to figure out through arithmetic what this is. So 5 plus 45 I think makes a nice pair to 50, and then 9, and so you get 59 minus 36. 59 minus 36, what's that, like 23? Yeah, there it is. Okay, so cool, that's it, and yeah, keep watching.